Hello everybody, my name is Thomas Trauch and we are dealing today with proposition 8 of Gottfried Leibniz's work on the arithmetic quadrature of the circle, parabola and hyperbola. And proposition 8 can be understood as an extension of proposition 7, where we prove that the same relationship which was proven in proposition 7 is actually valid for two other areas concerning the semicircle and the resecting figure. And this shall be proven with the same type of indirect proof which was applied in proposition 7. But let's start now. First of all, we're going to have a look at the upper half now only of the semicircular curve in order to make the whole thing a bit more legible. And we're going to place some points, of which we also draw the ordinates of the upper and lower point. And we're going to draw a sector in it, which is bound by the lines A, C1, the curve from C1 to C3, and back to point A again. And we already proved in proposition 7 that the relationship between this sector and what is now called a quadrilineum, shown here in green, is actually that the area of the sector is always half of that of the green quadrilineum here, which is bound by the two ordinates, parts of the axis and a part of the resecting curve. And this is actually the basis we're going to apply. And now Leibniz is saying or making a transition in order to generate two other areas concerning the circle and the resecting figure, which he wants to prove that they are subject to the very same relationship in the very same principle. And as the animation goes on, we see that it transforms what is used to be a sector into a segment now, a large segment, and what used to be a quadrilinear shape, it transforms now in a trilineum, which is this one here. And the proof is now about to show that the same principle applies as with the sector and with the quadrilinear shape, that also the area of the large segment is exactly the half of that of the large trilineum. And this is done in the same style as it was done in proposition 7 by applying an indirect proof, a deduction ad absurdum. And for the purpose of this, we're gonna go back a little with our C1 point in order to make up partial areas which we need to build our indirect proof. And we're gonna basically make the large assumption that the difference between the large trilineum and the large segment, or the double of the large segment, that this difference shall be some value set. And we also assume that the rectangle, which is formed by the A, B1, C1, G1 and back to A, shall be also a quarter of this very difference set. And we also can constitute easily that when we subtract what is now called here the small segment from the large segment, we actually get our sector. And in the next step we are going to constitute a similar thing for the trilineum, that when you subtract a small trilineum from the large trilineum, you will get a quadrilinear shape, our quadrilineum. And now we're going to go through a step or a sequence of determinations which lead to our proof, which lead to a step of our indirect proof where we again raise a series. And this first determination is saying that the area of the small segment can be assumed smaller than a quarter of the difference set. So we arrange our points C1 in a way that we can be sure that the area of the small segment is smaller than a quarter of set. So this is easily possible by placing the C1 point accordingly. So from this basis we go on to a second determination, where we say that we arrange the C point also in a way that also the small trilineum as a part of the large trilineum is also smaller than a quarter of the difference set between the large segment and the large trilineum. So in a third step we make a reference to proposition 7, where we stated, or where we've proven, that the quadrilineum, or the quadrilineum from B1, D1 down to D3, B3, B1 is actually twice the size of the sector A, C1 curved down to C3 and back to A again. And because this is the case, it follows that the difference between the large trilineum and the double of this sector must also be smaller than the difference set between the large trilineum and the large segment, because the very difference between the large trilineum and the double of the sector would constitute the same area as our small trilineum, which we already stated to be also smaller than a quarter of set. And in the next determination, number 4, we say that the difference between the double of the sector and the double of the whole segment must be smaller than the double of a quarter of set, because we said that the small segment is already assumed to be smaller than a quarter of set, and because when we make the difference of all the doubles of this area, so we double the large segment and subtract from it the double of the sector, we should get the double of the small segment, and hence we assume that this leads to a quantity which must be smaller than 2/4 of set. And now this allows us to again draw out a series, the elements of which are the large trilineum, the double sector, and the double segment. And we know that the differences between the two, as we just constituted in the 4 determinations we made, that the difference between the large trilineum, this one, and the double sector, the double of this area, we said that it must be smaller than a quarter of the difference set between the large segment and the large trilineum. And we also constituted that the difference between the double sector, that was determination 4, that the difference between the double sector, which is again this, and the double segment, which is the double of this, must be smaller than 2/4 of set. So this is giving us a series, and this series is of some order, but in any case, as we have shown in proposition 5, the difference between the large trilineum and the double of the large segment, which constitute our the difference between the outer elements must always be smaller than the sum of all differences. So, and the sum of all differences basically is a quarter of z plus 2/4 of z, which is making up 3/4 of z. So this is giving us the very same sort of equation which we were deriving already in proposition 7, that we get what is called an absurdum, namely a relationship which says that the z equals 3/4 of z. And this again is an absurdum which has only one case where of a quantity z where this relationship holds true, namely when z is 0. And that it basically means that between the area of the large segment and the large trilineum there can be no difference assumed. So these areas hence must be equal. So this proof is the very same principle as applied in proposition 7, and now we can use the relationship also on the large segment and the large trilineum, knowing that the large trilineum is exactly the double of the large segment. And Leibniz was proving this relationship between these areas because this relationship is coming in very handy later on when he further develops the other propositions dealing with the quadrature, and alongside also dealing with creating a notion and a notation for the actual calculus. And this is going to become very important in the next proposition. So that was proposition 8 for now. I hope it was not too fast. If so, then I encourage you to watch the movie again. As I said, it's quite essential and represents another very important basis on the road to the calculus. So I hope you enjoyed it, and I hope you see you next time around. Thank you very much, and bye-bye.